Welcome to In the Open with Luke and Joe. I'm your host, Luke Shantz, and here's my co-host, Joe Seppi. And a big welcome to our guest, Space Tech CTO, Naeem. Before we get to our show, don't forget to like and subscribe. Thank you for joining us for our conversation with the IBM Space Tech CTO and Distinguished Engineer, Naeem Altaf. We will be discussing the ENDURANCE CubeSat project, as well as the latest happenings in the space industry. But before we welcome our guest, let's say hello to our co-host, Joe Seppi.
Hey, Luke. How are you, my friend?
Good. How are you doing, Joe?
I'm okay. The weather's nice. The sun is shining. I'm in the Connecticut house with lots of trees, and I love to see the sun shining through the trees. It's really magical.
Yes, the leaves changing in the Northeast this year. I think it's a beautiful year. There seems to be a nuance to the colors, little oranges and yellows. Loving it.
Yeah, that's great. How's the weather down by you?
It was brisk last night. It was, it got down, I think, into the 30s. I don't think it was quite freezing, but we're kind of wrapping up the garden, getting the last vegetables, trying to insulate a few cabbage to carry on a little longer. So it's exciting.
Yeah, we're getting some freeze warnings up here too. So times are changing.
Why don't we find out what the weather's like in Texas and check in with our guest, Naeem?
Let's do it.
Hello, Naeem. Welcome to the show.
Thank you so much. Hello, Luke and Joe.
Hello.
Yes.
How's the weather down there?
The weather here is very nice. It's, I think, in 40s. It's almost 20 degrees lower than it should be. It's rainy and we're loving it.
Sounds great.
Yeah, I imagine when it's, you're sort of used to a lot of heat, getting that little bit of cool weather feels like a real treat for you.
Definitely, yes.
So, I would say this is your second time back on In the Open, but your third time back on an IBM Developer podcast. So welcome back. I think you're actually our first three-time guest to the IBM Developer podcast. So that's very exciting.
Thank you so
much. We're going to dig into the ENDURANCE CubeSat. But before we do that, why don't you give an introduction to our listeners who may not be familiar with your backstory?
Sure. You mean from my stuff or the CubeSat stuff?
Your stuff. Let's hear about you first.
Stuff.
Yeah.
Okay. All right. Cool. So yes, like you gave the intro. I'm Distinguished Engineer and CTO for Space Tech in IBM. This is my 21st year here, and we've been working for past 2 years in the innovation lab. That's what we do as IBMers, innovate in different areas. And we've been looking at what's happening in the space tech, how we can use what we have developed on the terrestrial networks from the cloud computing and how we can take it into the orbits. So that's what we have been focused for the last couple of years now.
Excellent. And I remember you telling me that your fascination with space goes back to childhood. You used to go up on your roof, look up at the sky, and this has been an interest your whole life. And now here you are, you're Space Tech CTO.
Definitely. It's a dream come true. Yes. Thank you.
I am curious, on that kind of backstory, how did you move into space tech at IBM? You've been there for 21 years. I assume you haven't been doing that the whole time. What was your journey?
So it's I guess, a transition or transformation, right? So I started, when I started IBM, we were working on systems, distributed systems, application monitoring. And after 5-6 years, we saw this beautiful campaign by IBM about Smarter Planet, right? That was before the things IoT days, right? That was very fascinating, that how the intelligent, interconnected, instrumented components will work together. So I moved into that area, and that opened up for me that what we can do with sensors and data and all that stuff. And from there, working with different aspects in the industry, I got the opportunity to work with NASA, the SETI Institute. And from there, it opened up to see, because from the background, my background is computer science. I'm not a, astrophysicist or something. So I thought, okay, since majority of the industry or things are software defined, so the principles and things which we have learned as computer scientists, we can apply in this industry as well. And since I knew space, I just tried to figure out how I can marry them together. And that's where we are today.
Oh, you're on mute there, Luke.
Oh my gosh. I was on mute. It happens to the best of us.
Yeah.
So, Joe, unless you have any other questions, I think we should dig into the CubeSat. So let's start off. What is a CubeSat? How did this come to be? How long have these things been around?
Sure. So this actually, I brought a CubeSat for you guys. So
Cool.
this is a 3D printed at home. This is a 1 unit. And I'll explain what 1 unit means. So the concept of CubeSat, it was around, I think, 1999, when the professors from the Stanford University and California Polytechnical State University, they came together and they were looking for how we can put something in the space so the researchers at university can, work with this. Now imagine almost 20 plus years ago, the cost of putting something like this in the orbit versus now. Huge difference. It's like almost exponentially, it's low now to put something in the space. But that was the main idea, that can students or researchers can put something together in the space and they can do research. So this CubeSat, generally, it's you will hear these things like 1U, 2U, 3U. I think it goes up to like 24, 36U. So 1 unit means 10 by 10 by 10 centimeter cube. That's what 1U is. And you can stack them up, build, depending upon your payload. A typical CubeSat has, it has the antenna for communications back and forth. It has the power source. You see these solar panels you see on the space station, those big ones, right? Similar on the satellites, they have, so they can gain power, and then they have compute on it, and compute for maintaining itself and doing the workload. And then a very common payload these days is the camera, because majority of these satellites are doing Earth observation from the low Earth orbit. So these CubeSats, the advantages are they are very cheap, relatively very cheap. I mean, a very professional one you can build for less than $1 million compared to the big ones, which are hundreds of millions of dollars. I also like to say that these CubeSats are like microservices. So for example, instead of building these monolithic satellites, you can build these small, which have a relatively smaller life, but they can get the job done. So that's what CubeSats are, and they're cheaper, they're fast. Their life is like between 3 to 5 years. From the sustainability point of view and from the environmental point of view, they can easily burn in the atmosphere because they are not that big. So we hear a lot about space debris, right? So it's not too much destructing the environment up there as compared to the bigger ones. So yeah, that's and then we saw in 2018 when NASA sent these satellites to Mars. Basically, again, going back to our cloud and cloud native terminology, sidecars, which we use in microservices. So they acted as a sidecar. So their main payload was traveling, and they had 2 sats which were next to it, and they were acting as a relay for transmission. So it's like, I'm just giving you to do this work. Let me focus on my major payload. And when the payload was about to enter the atmosphere of Mars, these both just went this way. And they actually took a selfie at that time, and they went and they burnt in the atmosphere. But that was an example of showing how these CubeSats, it's not a toy anymore. It can do actual real stuff. So yeah, that's the history of CubeSat.
So you mentioned when these were first sort of invented, the cost was very high, and now it's come down. So how is a CubeSat deployed?
Okay, so the cost, just to be clear, the cost was the launch cost was very, very high, right? It was almost, I think, like $25,000 per pound. Now it's $1,000. Because the reason is, think about that, in 20 years ago, we had space shuttle, and we have the Russian aircraft, and maybe one French, and ULA, very few. Now every 2-3 weeks, you see SpaceX going up. See, and there are many other launchers as well. So you have many more opportunities. Now the way it works is, if you look at a satellite, right? I mean the rocket. A rocket on the top is called a fairing. That's where the payload is sitting inside. So the way it works for these small sats is in this rocket in the fairing, they have their major payload, right? So they have like a multi-million-dollar, billion-dollar payload sitting there. But underneath there, they have extra space. So it's like, you know what? Okay, I can fit you in here. I can fit you in here. So they take these smaller CubeSats, And then there's another technique, they have deployers. So they basically, these things just goes in the orbit, and the deployer has these stacked in, and they just shoot them in the desired orbit. So the main payload still goes up where it's wherever it's going to MEO, GEO, or whatever orbit. And then in the LEO orbit, mostly they stay in the low Earth orbit. And just to for listeners, right? So there are three general orbits: low Earth orbit, there is a middle Earth orbit, and then there is a geosynchronous, geostationary orbit. So over here, we're looking at around 1,500 kilometers up. So around 400 to 500 miles in the orbit. That's roughly where the space station is also there, right? So they live in that orbit, in the LEO orbit. So that's how they get deployed. While it's going up, in the middle, it just drops a payload, and the bigger payload go to where it needs to go, and these smaller payloads gets deployed in the orbit.
This sounds like a ride-sharing scheme for satellites. This is amazing.
It does. It is ride-sharing, yes. And that makes the cost also come low, right? And it's a good thing, right? Because many schools, universities now can participate because the cost to entry is very low. Yeah.
And that's leads into my question a bit. Like, what do you see these schools and universities doing with them? What sort of research? I know you said photographs, I think, is maybe one common thing, but what beyond that?
Okay. So photograph, let's talk about Earth observation. The majority of the use cases are Earth observation. So for example, you're looking for, the melting of glaciers or deforestation, right? Or so basically the health of the planet. That's what majority of these CubeSats are used for. And because the thing is, like I mentioned, right, it's cheaper. You don't have many fancy sensors because some of the sensors are very expensive. So for schools, they can get a camera easily, right? And they actually use, like in this one, Raspberry Pi. That's a Raspberry Pi. And in fact, in our CubeSat, we will also using Raspberry Pi. So yeah, so it's sensors, so you can get you have sensors like magnetometer, sun sensors, so you can get the altitude, you can have your position relative to where the sun is, magnetometer, so you can orient yourself, you can get the magnetosphere around the Earth. These are typical sensors. And then the camera, then there is voltage, temperature, so the health of the solar panels, how much energy you're consuming. The power bank is very critical because you're not going up there to fix it if something goes wrong. It's not Hubble telescope, right? So you have to be very, very careful on how you're running your workloads. You're not exhausting the power. You don't want to burn your thing in the atmosphere, right? So these are the kind of things, and there's plenty of telemetry data which will come. And these are things which we will, as we talk about Endurance project, that's what we will like the kids to get engaged and do stuff.
And so is there a limited amount of power up there, or are you using like some solar bits to keep it? Yeah. Okay. Interesting.
So you have solar panels over there, and we will learn more about it. How much, for example, compute time we can get within 24 hours. We cannot run for 24 hours. So we have to see. Yeah. And do all the calculations. Yeah.
Are you using, is it a full-size Raspberry Pi, or are you using like one of the W, like the smaller? Full size? Wow.
The latest one with 8 GB. And we're also using something unique and new to industry. We'll talk about that later once we go deep into Endurance.
Excellent. So maybe now you should tell us about Endurance and the specifics of your project.
Sure. So, and one more thing for the listeners who are new to this, just for them to understand how this communication, because that's very critical. So here's another CubeSat, 3D printed. So here's a CubeSat, and it has, these are like the solar panels, and it has transmission, it has antennas on it. Now the way it works is, so you have a receiver and sender. So you have a CubeSat, you have a ground station, the antenna, and then you have, your receiver sitting where you're getting data. A very easy analogy is.
It was just this exact question. I just thought I would put it up on screen.
What argument do you have? Yes. So an easy analogy is if you have DirecTV dish network at home, right? Basically, that's your ground station. You have a receiver sitting in your home, and it's pointing to a geostationary satellite, and it gets the transmission. Your receivers decodes it, and you can watch whatever you're watching, right? Same concept. So you have, for example, if we are transmitting to the satellite, you take your digital data, like on a computer, you're doing something, it converts the digital to analog, then the signal gets amplified, through the antenna, because it's a radio signal, it goes up, and you have antenna. So over there you have a receiver. Now you do the reverse, right? You take the analog signal, you take the noise out, you convert the analog to digital, and then you have your data, whatever you are looking for, right? And there are a variety of bands. If you just type, Google it, right? The bands for communication, you will see there's a variety of bands which are used. Now in future, what we are looking for, these, as we are getting, the compute is getting dense and we are getting more sophisticated in types of compute we're putting in the orbit, these radio signals are very slow. Like the bandwidth is very, very low, right? And if we are talking about gigs of data, forget about it. So what the future is, all optical connections from ground stations to the CubeSats, and optical connections between the constellations. And you probably hear, if you follow different constellations, and if you read about Starlink, that's what the future is. They all have optical connections, and then they have ground stations. So this is where, for the researchers, or for people who want to think about, right? So think about this: when you have the optical connection compared to radio signal, even though it has low bandwidth and stuff like that, the hurdles in between, it doesn't care much if there's clouds and stuff like that. But if you have optical connection, if there are clouds, you're not going to get through. So now you have to optimize, because you're moving at almost 17,000 miles per hour. So you have to optimize, what is my next best ground station where I can do the dump based on the weather conditions. So now you can see how you can do like a digital globe, like digital Earth, where you can take information from different sources and make a good decision. So that's the future in terms of communications, which will be very, very much required if we are talking about higher, big data. It has to have a higher bandwidth. Now going back to your question, Luke, let's talk about Endurance project. So last year when we started our group here, and we were looking at we talked last year about the work which we have done for edge computing on the space station. So we were interested in doing stuff, but I also, while working in the space industry, I realized actually it's quite complicated to put stuff in the orbit, and for the right reasons. You don't want to anybody just start throwing stuff up there. There's a lot of paperwork, there's a lot of regulations, all that stuff, and then there of course is cost also involved. So I was like, if it's challenging for the people in the modern world here, think about the developing nations. It's very, very hard, very, very challenging, right? So the goal was, how can we serve multiple purposes, where we can do some research, have some state-of-the-art technology, bring some new concepts, and then also do tech for good. So the first idea was, okay, if we can build a CubeSat, let's focus on edge computing, because edge computing is huge these days on the terrestrial stuff, right? But now when we are talking about, you saw probably a lot of news past 2 weeks, people are trying to they're building a new ecosystem in the low Earth orbit, right? So you need a lot of compute, what you can do over there. So we said, okay, if we can do edge computing, if we do research with these sensors over there, and for the state of the art, we want to take the concept of cloud native, like basically microservices and Kubernetes, into the space. And that's where we engaged with our brilliant developers from Red Hat. We said, you know what, we need an equivalent of OpenShift for the Raspberry Pi, so it can fit on that small footprint, so we can send it into the space. Now here's the idea. As we all know, the cloud in general, the hybrid stuff, right, where it's a combination of cloud, on-prem, different areas. From developers' point of view, I don't want to be in this game of understanding, is it edge, is this different, this. I just want to do my development, build my code, build my container, and push it out. Now that pushing out to target, it can be on-prem, in cloud, on the cell tower. So who cares? On the Mayflower ship, wherever it is, right? From a coder point of view, I just did my development, built the container image, push it, wherever the target is. Now we are extending that target from the ground to space, right? So we have a Kubernetes platform, which will be running on this CubeSat. We actually already have running on space station, which we did the project last year. So now we will have in our CubeSat, so you will be able to build your code and push that code to run on a microshift. It's called Red Hat Microshift project. It's an open source project, which you can see the URL there. And that's what you're going to use as base. to run our payloads on this CubeSat. Now, going back to Tech for Good. So while we are doing this, we're like, okay, let's give opportunity to everyone on the planet to be part of this. So think about this, like you are a kid sitting in remote parts of Africa somewhere or in Asia, right? Today, these days, most of the people have access to some sort of network connectivity and some sort of compute. So think about it, you're sitting in somewhere and you write a small piece of code, as simple as Python code, and you push it, it goes to, you submit to us on IBM Cloud, and you push your code, like I mentioned, explained, to the ground stations all the way up to the CubeSat. Now your code is actually running in space on the CubeSat, and then you get the results back, right? And we will provide like the specs, like all the sensors I mentioned. You will be able to take a picture, right? And we have some other fancy things which we are thinking about, like sort of a assistant, digital assistant on our website, where you can go and ask questions. Hey, CubeSat, where are you now? What was the last thing you saw? Things like that, because we will have access to data, so we can come up with those answers, right? So yeah, that was the whole idea. Let's democratize the access to space for everyone, right? And for that purpose, you very well know, or Luke and Joe, right, that IBM has this PTech program, which is all a global program. And we engaged with them earlier this year. We explained them this is what we are trying to do, and as expected, they are very, very excited. And so now we are in process of building a curriculum, and we will have a sort of like a competition internally. So we can pick 5 schools initially for the next summer, and so then they can participate and be part of this. And by the way, our launch is expected April. It takes about a month or so for it to stabilize and start receiving information and sending. So looking at summer next year.
And what age groups for the schools are you looking at?
High school.
Okay.
High school kids, yes.
Cool.
But later on, it can be, because Python is a relatively very, very easy language, and kids at these days are learning at, in their middle school or something. So it's open to basically anyone who can do it.
Yeah. Cool. So people can learn more at this link, .enduranceinc.space. They can learn about all that. How to get your code up there and learn more about the schools and all these things.
Yes.
Okay,
we have quite a bit of information on that link. And then another thing over there on that link is, just for fun, we will issue you a boarding pass. If you go and register on that site, like basically what registering means, you're getting a boarding pass, and we will send your name on the CubeSat when it launches. And you get and the boarding pass number are generated by our quantum computer.
Wow. That's really cool.
And just to give folks a little background, Naeem mentioned PTech, which I don't know the exact number of schools, but there's many of these high schools throughout the country, and I believe the world even. And the students graduate. I don't know if they actually graduate with the associate's degree or just experience, but a lot of them get jobs right into the tech industry in IBM and elsewhere. And, I know Joe and I have had folks on our team, and I currently have someone on my team now that's a graduate of PTech. So it's a really excellent real world results program that gives the adolescents a real head start into getting their job in tech.
Yes, it's a very good program.
Yeah. We have a question here. I wonder if this ties into some of the links that we have queued up as well. I don't know if I'm getting off track here. So what is future of space technology at IBM? We're talking to the CTO, right?
So the future is great. I mean, future is what we can make it, right? That's what I believe in. So if we are looking at, again, the listeners who are interested, go to Twitter and look for hashtag IAC 2021. It's one of the biggest space conferences, which just finished last week in Dubai. And if you just go and look at hashtags, you will at least get a sense of what the industry is thinking, what the major space agencies are thinking, right? That gives you an idea. So if you are, let's say if you're a programmer, it's a huge thing, right? Because computers are everywhere, programming is everywhere, right? So from that angle, how you can be involved. from IBM's point of view, I mean, in future, 5 to 10 years, right? The quantum computing, that's going to play a huge role in this industry. Think about the trajectory optimizations, or the how the data is transmitted, how the data is secured, right? That's where the quantum, all the optimization. So you again hear this big challenge in the industry about cleanup in the orbit, because as you probably have seen, there's a lot of junk in the orbit. So like that traveling salesperson problem, how do you optimize? You have limited fuel, whatever spacecraft you're going to send to go do cleanup, right? How do you find the best possible target and do within your limits of your fuel or whatever, right? So this is where, as a computer scientist, it's very exciting to see how the algorithms are going to play around. The other area is data and AI. And data and AI is wherever there is data, AI is attached to it, right? So like I mentioned, Earth observation, there is a majority of these satellites in the low Earth orbit. So just to give you another, explain again, in low Earth orbit, because of the latency is low, most of your satellites are providing internet connectivity, cameras, data, voice kind of thing. That's why you hear about Starlink, right? Providing a whole network in the orbit. Then you have MEO, that's where your GPS systems are. Then you have geostationary, that's where your TV satellites are. Because you don't want to go, because you know the rotation, right? Why it's in geostationary, because it matches the rotation of Earth. So when you put your dish out, you're not running out and moving your dish, because it's exactly pointing at that satellite, right? So it's in motion with that. So yeah, so that's where the satellites in the lower Earth orbit for Earth observation, all this data which is being produced. Now think about let's think about the natural disasters, right? Which we see quite unfortunately often now, like the fires and these hurricanes, all that stuff. So let's take a fire happening in California or Australia, right? So your first responders, they are getting to the site. First of all, the communication lines are down. So that's one use case where you have, from the satellites, you have communication, so you can communicate with your team or whoever you want to communicate. Next thing, you want to understand which area should we go after first, because it's limited resources, right? So now not only you have limited information from the ground, but you have satellite which is watching from the top, and these satellites today can scan the whole globe in like twice a day. So your data is only 12 hours old. So you have this extra help from the satellite imagery which is telling you what's happening there. So all this data has to be processed. So you, as a computer scientist, data scientist, huge opportunity how you take this extra layer of information and you do merge with the other information you have on the ground and make sense out of it. So that's where I see a huge opportunity for even people who don't have the background in space. As computer scientists, you can be part of it.
That's so interesting. And I remember you had mentioned to me in a past conversation another aspect of the space industry that's a really big deal that actually taking place on the Earth is just the logistics and supply chain of it is a massive industry. And there's a lot of, it's something we don't necessarily think about, but it's really mission critical stuff, knowing the provenance of where everything comes from and making sure it's authentic and it is what it says it is. So it's really such an,
Sure.
There's so many opportunities that you may not think about that involve space.
Just simple analogy, right? So let's say, you live in your home, right? And there are a bunch of sensors, you're watching you, all that stuff. Let's take the roof away. And I sit on top of that and I watch you every day. After like a 30 days, I exactly know your pattern, what you do. I have an exact idea, but we all have a pattern, right? So that's what satellites are doing. From the top, they're watching, right? So for example, you're probably hearing right now, there's a big pileup of ships in California, right? So you can do the math. I mean, it's a supply chain big challenge. So if stuff is coming, it's not getting removed from the ships, the trucks are sitting there, it cannot move forward, right? You can just connect the dots and how it can affect the end user, right? And that's an extra view from satellites. You can see, okay, you can see ships lining up, okay, what's going on here, right? And then the biggest help is, okay, then you can talk about like the melting glaciers and this climate change, right? And this whole climate stuff which is happening. I mean, if we can create a digital twin of Earth, that's so cool. I think that is the cool part. You have a digital twin of the Earth. What does it mean? It means that you have enough near real-time data from sensors which you can replicate in a digital way. So you know what's happening, where the weather is bad, where the ocean levels are going up, some stuff is heating up, all that stuff, right? And that's where satellites can really, really help.
Another thing along with the satellites related to financial industry, I'm trying to remember if I read this in a book or if I saw this on the show Billions. I can't remember, but hedge funds and financial analysts, they'll also use this for exactly like you're saying. They can watch the ports, they can watch companies. I mean, obviously there's military intelligence aspects there as well, but you could actually make predictions about financial markets by analyzing the satellite photos.
That's what they did last time when the crash happened in just after the COVID last year in March, April timeframe, right? Exactly that. They saw a pile up of stuff and they're like, something is about to happen. Yeah. Then another very cool example I have read about is you see these big oil tanks, right? Which are in the, wherever, the crude oil is coming out. Those roofs are floating roof. So let's say the sun is out. From there, you have a shadow created if the roof is a little bit down. You can calculate the angle. So you can know what is actually being reported, what's real is. You can do that calculation just from the satellite.
Wow.
Amazing.
Mm-hmm. It is. It's a little scary even.
Yeah. Exactly. Yes.
Precision agriculture is another one I've heard of, where you could, from the satellite imagery, you can identify individual plants and create custom recipe for how individual plants in a field, like say the IBM example I heard was, I think it's Gallo wine. They will use satellite photography and analyze it and be able to make like plant by plant recommendations about how to service that field.
Mm-hmm.
Wow.
Almost every industry vertical you can think of, this extra layer of information can help. Almost every industry.
It's awesome. I think we take for granted how much access we have as, just individuals too, being able to go on any of these mapping programs and look anywhere in the world. It's obviously not real time, but if folks are interested, it's like we take it for granted, but we have access to a lot of these tools.
So the Endurance mission is democratizing access to space. Like, what do you see happening outside of the U.S. and Western, I guess, advanced countries? What else is going on in other parts of the world?
Sure. So one nation where we are seeing a lot of innovation in this area is the Emirates, right? Their space program. So the two or three major ones I see, one is the Australian Space Agency, and one is Dubai. You saw they put the orbiter in Mars orbit this year. So and now they just announced like a month ago that they will have like 7 more missions coming up, right? So that's a lot of innovation is happening there. Australian Space Agency. There is a big rush to get to the moon, right? The Artemis program. So there's a lot of because this time when we go to Artemis, right? They want to stay there. So think of it as like you're building a next gen smarter city on the moon now. So whatever you need for a city, you need over there, but it has to be autonomous. You can't just say, let me go back to Earth, pick something, come back. You can't do that, right? So I mean, you can maybe, but it will be very expensive. So you have to think in that paradigm, how we build stuff which is self-sustainable, right? Autonomous. You have these rovers, they're moving around. The security aspects, of course, and the other big thing which is happening, which big announcements happened last week at the conference, was this building of this whole commercial space stations. Because space station, as we know, our beautiful ISS, the end of life is 2024, and it might extend 4 more years. So let's say 2028, but eventually it will, it will be decommissioned. So what's next? So China is building their space station, but there has to be more, right? I mean, so like now this is where the private sector is coming up, right? Like the Blue Origin announced that orbital reef, right? And then we hear from the nanoracks. They're also putting stuff there. And there's Gateway Foundation. They also want to put stuff there. These all things, if planned, in next decade or so, in next 10 years, you will start seeing stuff in the low Earth orbit. So I think this is where the private sector, the commercial, is going to help a lot. They can move, I believe, much faster, right? Again, by working with the experts from the agencies to build this stuff up. So yeah, that's what I see a big stuff happen. The Artemis program in general, and I think the test flight is February next year, when they're going to do a solo flight. And then we hear about all these commercialization of space station. Yeah,
it sounds like it's going to get a little crowded up there.
it will. Yes.
What do you do about that? And I feel like I read something somewhere. I can't remember what it was exactly, but somebody starting to, one of our I don't know if it was our Air Force or Space Force or whatever, starting to regulate space more. What's going on in that area?
So there's lots of discussions happening about the policies for space, because right now it's kind of wild west, right? You can just, whoever got the rocket, go and put stuff there, right? And there's many other reasons as well, as you can imagine. But yeah, I think for all of us to succeed, we have to work together. Like I said in one of the conferences, this is a team sport. We cannot just say only me and Luke are going to play, and Joe, you're not a cool kid, you can't be part of this. We have to work together, because everybody loves space. Space is not only for one country, it's for the whole humanity, right? If we all work together, we can do very amazing things. But I think there has to be, right now there are like you saw there were some something signed for Artemis for going back to the moon, but few nations did not sign those contracts, right? So there's a lot of things happening right now, but I think eventually they will have to come up with the policies, and they work together. Otherwise, it will be challenging. Yes.
Yeah, I found it really quickly. It was the United Nations that apparently is looking at creating rules for space, yes. And it's interesting. Yeah, I think that quickly glancing at that article, we're talking about like a variety of commercial sort of things and research, but they're talking about some military related stuff and yes. Keeping the peace in space. That sounds like a whole nother topic, huh?
Exactly. And without naming anything, it was an article which came 2 years ago, and that was really fascinating, that how some nations have satellites which are nested. So one satellite has a satellite inside and has another satellite inside. So they're just this is all for surveillance and all other purposes, right? But the people are coming with different techniques, right? So I think it will be interesting. We don't want to pollute our beautiful sky, because that's one thing. Now the other thing you hear about this James Webb telescope, which is going to go in December, right? Which have been delayed for so long. And and then we have these $1 billion telescopes which are being built in South America. If you look at their size and how gigantic they are, right? We don't want to pollute they bring so much information for us. So if we pollute stuff, it will be very challenging, because all this noise is creating noise in their data in the orbit. So yep, that's the thing.
Yeah. I heard some. Sorry,
go ahead, Joe. Okay, I was going to say about, I know the astronomers were really upset with SpaceX and the constellation of satellites, because it was, and I think subsequently they have started to make them darker, so maybe they're not as reflective, but I imagine that space and moon telescopes are probably going to be the future, because sounds like with so many satellites going up and so much activity in orbit, it's going to be rough on the astronomers.
We have to step out of the low Earth orbit, right, and go a little bit further down to, it seems like that. But that's, of course, it's very costly, right, to do those kind of functions. But we have to meet somewhere in the middle. Innovation is good, but we can't disrupt other things.
What were you going to say, Joe?
Oh, I was just I think I was reminded of another thing that I had listened to on NPR about taking some sort of telescope up on a balloon and then bringing it back down, if I remember correctly. Which, I mean, I guess, we need to be creative about how we get out there.
Mm-hmm.
Yeah.
There's even people who take the small rockets, like the sounding rocket, and put it on a balloon. So the balloon goes up the 90,000 feet, and then you can launch your rocket from the balloon. It's called a raccoon.
Nice.
It's a ridiculous name.
Yeah. Didn't you put something up on a balloon once, Luke?
Yes. So this is a great story, actually. This is one of my favorite things I've ever done. Is I was like friends with and like an influencer for early MakerBot, and it was so they had gotten a fancy laser scanner and they went around scanning all these celebrities, and they scanned Stephen Colbert's head, and then we did like one of those where you put the camera and then you have kind of like a chopstick sticking out with your 3D printed Stephen Colbert head on it, and then you send it up, and we did it. It was very hacky. Name, you'll probably laugh at us. We did like a cell phone with like an app. It was like a candy bar phone with an app that would like ping back the GPS coordinates. So we launched it in Newburgh, New York, which is right by Beacon. If anybody knows, there's a big museum up there, and it ended up, I think it went 90 miles and landed in Connecticut, and we had to like climb a tree to get it. And it's, if anybody hasn't done this, it's a really interesting, fun project, because you've got to do all your calculations. You got to have the right amount of helium and do all your calculations, because you have to get it, because as the balloon goes up, it expands as the atmosphere gets thinner, and then it reaches a height, and then it bursts. So if you put in too little helium, it's not going to burst and it's just going to fly away and you'll never find it. If you put in, too much, maybe it'll burst too soon and you won't get that awesome video or photography that you want to see the curvature of the Earth. So we did this for the Stephen Colbert, and it was a lot of fun. I would love to do it again.
I'm sure it must be fun. Yes.
That's great.
People use GoPro cameras now. I have seen they stick on and they take the pictures of the horizon. Yeah, it's pretty cool stuff.
This was so long ago. I think we used a flip cam. If anybody, I don't even think people remember flip cam is like the MySpace of GoPro. It's it's quite old now. Yeah.
That's funny. So I'm curious, you were talking earlier about containers and how to deploy your code and using this new microshift. Like what does that look like, and what are the limitations of the code that you can actually put out there? I'm curious of the limitations of what you're doing there.
Sure. So I think the limitations are, of course, bounded by the hardware, right? So I think this Raspberry Pi is quad core with 8 gig of memory, and it's also reading telemetry information, camera. So we have to be careful how much space we give to the container, right? So we are doing a lot of right now testing experimentation, but the code is it's not that heavy, because, for example, the only high processing is when you're doing inferencing. So for example, one of our AI model will be, so you take a picture, and majority of the time the Earth is covered with clouds. So the model can say, discard this image because I saw clouds, bunch of clouds. So that will be a little bit of CPU intensive. But then microshift containers, it will be lightweight, very small containers where you're running the Python code, and it's looking at different kinds of telemetry data and doing calculations. So this also brings up another point, right? So as we know in general what Kubernetes platform can do, right? I mean, it's an orchestrator. It's like I call it like a digital data center, where it tracks everything inside and maintains and high availability and all that kind of stuff, right? Virtualization stuff. Now we think about like a hosted multi-tenant solutions on the CubeSat, right? So you have you can say CubeSat as a service. So I have a CubeSat hardware there, and let's say we have 2 or 3 of these Raspberry Pis. If we have a little bit bigger unit CubeSat, and you can run multiple workloads, right, within different computes, or you can run within the same compute because you have Cube there, and you can have different namespaces. You can do interesting things. So that's the idea here is, I mean, this is again, research experiment. There is a very there's a big conference which happens in Utah for CubeSats every year, small sat, right? The idea is to go, because there's developers there. This is for developers, right? To expose developers to say, you know what, we have this Microshift platform for the CubeSats, which you guys all working on. Try it out, right? As you're developing your next gen workloads, take advantage of this lightweight Kubernetes platform, which can now run on a CubeSat. So we want to create awareness for the developers and say, here's another way, as because the compute is, keep on getting better and dense. And so in a year from now, you will even have probably more powerful compute there, and you can do more things for more people. So you want to take advantage of that. The hosted and multi-tenancy and running multiple workloads.
Yeah, that makes sense. That makes sense.
What I find so exciting about this whole CubeSat and the fact that it's Microshift is, it's fun. It's great to talk about it, but I love that it also relates back to like all the terrestrial things we're doing every other day, and edge is such a big part of so many industries, and is a big part, will be a bigger part. And I love that this is like a use case that we get to explore. That's not just like some edge use case, to play pun on words there, but it actually applies to everything else. So it's so fun that the same frameworks that we can use in an instance like this could be in the factory down the street, in that field, in an agricultural deployment. It's really exciting. I love when we get these sort of fun thing. It's rare that you find something that's so fun, but that relates to the the everyday work that we do.
And for the listeners, right, if you are more interested in these kind of extreme edge use cases, because I believe edge computing is the evolution of cloud. So cloud was done 10 years ago or 15 years ago, right? Now we are headed towards the edge. We do this every 2 decades, right? We go distributed, we come back centralized. When we go distributed, come centralized, right? Now we are again going distributed. So think about all these missions which are for space. As you can imagine, the challenges are the power. You don't have enough power, which will affect your computation power, everything. And the next biggest thing, or the biggest thing, is the network, right? The network connectivity, the latency, right? How do you tolerate that? How do you build your application solution that can tolerate this kind of delays and everything, or intermittent connection? So if you are sending, let's say your edge is on the moon, right? Right now your edge is outside your home, or on some autonomous car, wherever, right? But now it's sitting on the moon, and you have limited bandwidth, and you have a delay, and there are hiccups in the network. How do you push your stuff? Because your stuff on the moon is autonomous running, and there are other players or actors over there as well. So how do you know that it's secure? The model you push there, the signatures you have, it's all secure, that nobody, another autonomous vehicle comes and hack you and make it work for them. That vehicle which you sent over there, that's working for other folks, right? So think about these things. These are the use cases which will come next. If you can solve these use cases, then use cases on the ground will be relatively much easier to solve, because we don't have these kind of challenges, right? So it's always look for the extreme use case. If you can solve that, the rest becomes easy.
It's interesting. It reminds me of like in the web programming space, thinking about like offline first development. When you're building a mobile app or website, you want to prepare for spotty connections and things like that. And like you said, your edge might be on the moon, and maybe it's a cloudy day. Who knows? You got to be prepared to handle that sort of stuff, I suppose.
The other thing, just to mention one more thing, is, as you probably know, the term you hear about this thing called air gap environment. Basically, it's fully isolated, sitting somewhere where things, you can't just run your command where it's hitting the internet and getting you libraries, whatever. That's what we developed for the space station, our edge computing. And shout out to our developers at Microshift. They built this Microshift to be an air gap environment. So once it's deployed, because many of similar kind of platforms at this smaller scale, they require touching the internet. Mm-hmm. When you are in extreme use cases, you can't do that, right? So they have done a great job where once I put a Microshift there, I'm good. I don't have to go and ask internet, hey, I want something here, right? So it can run in isolation in an air gap environment. And that's very, very important when you're working in these extreme conditions.
Yeah, interesting. How long has the microshift stuff been around? That's pretty new, huh?
Yeah, a month ago, it just
Oh
was,
wow.
yes. We've been engaged with them for a year now and talking about this stuff, but it's there now. So it's going to keep on getting, it's very new, right? So
Yep.
we are just using the fresh stuff and sending up there, right?
Yeah.
But it will keep on improving, of course.
Yeah, of course. Very cool.
I have a question about the CubeSat itself. So is it like a seal? Is it going to be sealed? And what's inside? Is it air? Is it nitrogen? It's not just open to space, I imagine.
I was wondering about that too. Yeah.
Okay, so let's take a look at this thing. Okay, so this is a CubeSat, right? Yes, it is sealed. It is it is not like this. So it's sealed, and then basically, let's say if this was a 1U, these all four sides will be sealed by the solar panel. So it's totally sealed system. Yes, and the reason for seal is to protect this compute from radiation, because it will burn this thing in a second. So there are two techniques, right? One is a traditional technique where you had these radiation hardened compute, which is very proprietary, special. Even the processings are, it's not like off the shelf like Intel or ARM thing. But now the industry, because that limits you, because not your all software programs can run on there. You have to have special compiled programs for them and all that stuff, right? Now the industry is saying different way. Okay, you know what if we radiation harden the enclosure enough that off the shelf compute like this Raspberry Pi can survive? So there's multiple techniques, right? Either you get a compute which can take care of itself, or you put in a box which will take care of that compute, right? So but still, yeah, it is totally enclosed, and some have propellant. It all depends upon, because most of the CubeSats which are sent for research school purposes, they just live off the solar power, and that's why the life is between 2 to 3 years, and that's enough. They do their stuff and it's done. But if you want CubeSats, which you want to stay for 5 years and you want to maneuver them and stuff, you need fuel over there, and that becomes more expensive. The requirements are much higher to go through and check marks all those lines. It's a little bit complicated.
And is it just
And
regular air inside, or is
there's
it
no
is it going to be like nitrogen or something?
No, it's no nitrogen.
No. I had heard that there was, like, when they have server rooms that are like on offshore platforms, they'll fill them with nitrogen so that it's like non-corrosive. And I wondered, like, what if there's moisture in there up in space? Is it gonna, like, is that gonna be an issue? Is it gonna freeze, or like what's? I was just wondering.
I'll check on that. How do they? It's a good question. How do they prove that? Seal that from that point of view.
Yeah.
That's gonna be about episode 4.
Yeah. And then, so how long do they last up there typically?
2 to 3 years.
Okay. And then what happens? Yeah. It eventually burns up, or
the thing is, since there is no, think of this, there is, let's say in simple words, there is no motor there to keep it up, because with the orbital drag and everything, it's losing altitude, right?
Okay.
So there is no motor there to say, go back up to your orbit.
Yeah.
There's nothing there. So eventually in year, 2 years, and then also the components, they start failing, because this is not like $1 million thing. Kids build this thing for like $1,500.
Yeah.
The stuff, right? That's why if you build like the commercially small sets, we can call them, they last a bit longer, like 5 to 6 years. But now here's another challenge. Since the compute, camera, everything changes so quickly, technology, right? So you cannot, if you're in competition with other companies who are putting stuff there to do Earth observation and sell that data satellite, right? You cannot have your camera which is 5 years old, right? So the life is, they recycle them every 3 years.
Okay.
Yes.
Interesting.
I have another question. So you mentioned that there's like a deployment mechanism that's going to be launching these things at the right time.
Yes.
And does that take into consideration like the orientation of when it's launching, so that the camera's facing, it launches it, like throws it out perfectly with the camera in like the direction you want, so there's no way to like sort of reposition it once it's going?
It just says Seriously, if you have seen the there are videos. It shows it's there is from nanoracks. There is an arm there where they just load them and it just shoots right to whatever altitude you are aiming for. But then there are like these magnetometers inside. There are sensors inside which will start to stabilize it. It will it's like tumbling over there. It's because you have sun sensor, you have nadir sensor which can look down. So all these sensors are helping you. Okay, buddy, just calm down. Let's come into our proper orientation, right? If that stuff is not done properly, then your CubeSat is to the contest doing that, and basically you have lost the satellite.
So it's got like internal stuff that sort of stabilizes itself and orients. Interesting.
Yes.
Is it like a spinning disc kind of thing to help stabilize it? I've seen some video of they had like it was almost like CDs on different access on the space station, wasn't it? You could like fly around with it.
Yes, the different techniques, but they try to like stabilize. Otherwise, it's like quick because it's moving at 17,000 miles per hour.
Yeah, that's wild.
Yeah, and it's like this going like right.
Yeah,
you want it to stable. Look at something.
Yeah. Yeah.
And you mentioned the bandwidth. What's the bandwidth going to be like?
So the bandwidth is low, right? Because these are just using like K band and Ka band. So this is like maybe 1.5 or 2 meg. That's the bandwidth.
That's not bad.
Yeah, it's not bad. But the thing is, if you have an image, right, then it becomes a little bit challenging. So then you have to come up with techniques where you only send down what's meaningful, right, and decompress it and all that stuff to push it down. Yes.
Yeah. Interesting.
That is really interesting. I imagine too there's some trade-off there, like versus your compute time versus your bandwidth. Do you find that sweet spot of like compressing it just enough and that wow.
So you have to calculate all that. What's the most optimum way of transmitting information? Yes.
Well, we're running low on time. I want to make sure that we touched on all the things that you wanted to make sure we touched on.
No, I think we touched on what the new things we want to go give back to the developers, but the tech for good areas we're trying to do with the schools and P-Tech program in general. And we talked about the CubeSat. We talked about what's happening in the industry. But yeah, I mean, it's a very exciting area. I mean, I'm very interested, waiting anxiously for the Starship, right? Let me tell you a funny story. So 2 months ago, when they stacked the Starship up, remember over here. So it was done on Friday morning. So I saw that. I'm like, we have to go and see this stuff. It's like 5.5 hour drive from Austin. So I called all my friends, and two of them had work on Saturday. I said, just dude, we are going to see this thing, right? And they called their employers, I think. Then I was looking, and I didn't check the TV or anything or channel. And at night, I was just looking at, because there's a live feed over their camera for the Starship, and the Starship was not there. I was like, what happened, right? And then I started reading. It said they only stacked it up for a few hours just to test the stacking, and then I took it off, and then they will do it again. And then I had to call all my friends, like, oh, we are not going tomorrow. We are not driving 11 hours just to see. But I think in a month or so, they are saying it will get stacked up, right? I think it's, if you just look at the pictures, when they compare that the people who are building the Empire State Building, the workers, right, just sitting on this, it's mind-boggling, right? How big this thing is.
Yeah, it's amazing. Very cool.
I want to go see it too.
Me too.
Come over often, we'll all go together.
Yes. Yeah, sounds great.
I'll try to. Hopefully, there'll be a conference that week or something. I could get an expense report in.
Just a meetup. A meetup is good enough.
A meetup, yeah. Well, we are out of time. This has been time goes so fast on this show, and especially when we have such an exciting topic like this. And really appreciate you taking the time to speak with us and our listeners. And it's such an inspiring project and just space. And I feel like the one takeaway I got was like, wow, it's amazing how from like a software development foundation, if you're passionate about any of these other topics, like there's a way to be a software development in finance, in physics, in space, in quantum. So it's really inspiring, amazing story. We'll definitely have to have you back, April, like maybe a month afterwards, once you stabilize and you get some pictures, come back and we'll do it again.
Yeah, sounds great. Thank you, Naeem.
Thank you so much.
Yeah. Cheers.
Cheers.
Cheers.